Let's spend a couple of moments discussing an important topic as we get started. And in this case, we're going to talk about EMF and terminal voltage. Now, the term EMF, the only reason I bring it up is because Gene Coley mentions it, but EMF actually stands for Electromotive Force. And it is an outdated term. You'll still hear some of the old engineers and physicists talk about it, but it really is an outdated term. It does not really identify or describe the actual function. This was started in the 1800s when they were first looking at current, and they came up with this term electromotive force. But you'll still see it. I try not to use it, but I just want to let you know it is an outdated term, and all it refers to is a battery. That's all it's referring to, or some kind of source, in this case a battery. So when you see EMF, just think of a current source or a voltage source. Now in this chapter and in this course, we're only going to be talking about voltage sources. Current sources are a different type of supply of current, but we're not going to be discussing that so much. So we'll be talking about voltage sources in this chapter. And the units, as we've talked about previously, units of a source, it has a voltage potential across it. So the units are in volts, and that's the letter V. Now, typically we use different subscripts to describe whether we're talking about an identifier for a specific battery or source, or if we're talking about the units. If you see just a V, then typically it means the unit of the device or the source. If you're talking about the source, you'll see some kind of subscript to identify that source. Now, I will grant you these variables and subscripts do get confusing. You have to keep things straight, and it's why I don't know. I just know that you have to keep it straight, and I'll walk through examples, try to help you do that. Now, sometimes you'll see the letter E used for voltage sources, and it's common to do that, but not always. So, but you may see it, and it usually is kind of some squiggly E looking thing that you'll see. Now, another topic that we need to understand is this idea of modeling. And what we do in modeling is our first try, we assume that everything is ideal, everything's perfect. We assume perfection. That means that batteries maintain their terminal charge, or I mean, terminal voltage. Which, when we talk about Ohm's law, we have V equals I times R. what they're saying is that if this resistance, if R goes to 0, then the supply can source an infinite current. So if I'm looking at something that's perfect, this 12 volt battery will maintain 12 volts even if the resistance goes to 0. It just means that the current will have to go to infinity. Resistors don't change in value. And we'll talk about capacitors and inductors later, what actually happens with those. I mean, capacitors, we just assume that they're perfect capacitors. So inductors, we'll have to talk about that one later. But so capacitors are perfect and can maintain charge separation at infinite potential. Okay, so this is the idea of modeling. This is our first try, and that's what we're going to be dealing with. Our second try well, we begin to model the model. So we start to model into our imperfections into the circuit. And in this case, I have a battery. I would consider it to be perfect, but no battery is ever perfect. So in this case, I'm going to model some resistance inside the battery at 0.5 ohms. And that's typical for most batteries, about a half an ohm of internal resistance. And so this is going to have an effect on how this circuit performs. This model of the imperfection of the potential, this would be basically looking at this whole piece as a battery, starts to have some very, very noticeable effects on the circuit. And here we're going to take and look at the potential over across a resistor, that 65 ohm resistor, as the 65 ohm resistor goes down towards actually that would be 55, starts to go down towards 0. So if we have this, and there's a graph of this in the book, or in the notes I mean. So we get our axis set up here. So we're going to go down to 0 volts, and here we have 12 volts. And if this is ideal, if this battery is ideal, then let's change a color here, make it a little colorful. Then my voltage potential of that battery is pretty much going to stay. I mean, this marker likes to do squiggly, but hopefully you get the idea. It goes straight across, right? But if I add in the model of the ideal imperfection, that internal resistance, what happens is that the potential will maintain pretty close to 12 volts. And then once you get down to this very low resistance, you'll see it start to dive down towards 0. And we'll talk about why that happens. But the red is the actual, real life. The blue is the ideal. So this is the basic concept of modeling. There's different levels that we haven't talked about, but the basic idea behind modeling is to look at the ideal and then model in the actual imperfections into the circuit. And circuit simulators get pretty close. A lot of times they're within 90% accuracy of what you would expect to see.